Welcome back. We know by now that semiconductors are a very important kind of material as they have electrical properties between that of conductors and insulators. Now there are two types of semiconductors, intrinsic semiconductors and extrinsic semiconductors. Let us first revisit intrinsic semiconductors. Intrinsic semiconductors are basically pure semiconductors. By that it means that no impurity has been explicitly added to them in order to modify their properties or characteristics. Therefore, pure semiconductors or intrinsic semiconductors are also called undoped semiconductors. The conductivity is low at room temperature, and we also know that the conductivity of semiconductors is heavily dependent on temperature. At increased temperatures, more valence electrons are able to break free from the atomic structure, and because at higher temperatures there is a higher availability of free electrons for carrying current, therefore with an increase in temperature, the conductivity of semiconductors or intrinsic semiconductors increases. Now we know that intrinsic semiconductors or semiconductors are elements from the fourth group of the periodic table. So basically semiconductors are those materials which have 4 valence electrons. Now the most typically used semiconductors are silicon and germanium. Both, as you can see, even though they have different atomic numbers, with silicon having an atomic number of 14 and germanium having an atomic number of 32. But both of them, because they are elements of the fourth group of the periodic table, each of them have 4 valence electrons. Then silicon is much more widely used as compared to germanium. Now here I leave this as an assignment for you to find out that why silicon is a more widely used semiconductor material as compared with germanium. Here we look at the atomic structure of semiconductors in more detail. We take silicon as an example because, as I've already told you, that silicon is one of the most widely used semiconductor material. We also know from previous study that atoms have this desire to have 8 electrons in its valence shell in order to acquire a certain atomic stability. Therefore, a silicon atom, which has 4 valence electrons, it shares those 4 valence electrons in covalent bonds with its 4 neighbors. As you can see in this figure in the middle over here, that each silicon atom forms 4 covalent bonds with 4 neighboring silicon atoms. This way, of course, a silicon atom is able to complete its valence shell and acquire that atomic stability which atoms want to achieve. Now this image here in the middle or the one here in the left are simplified representation of the covalent bonds existing inside a semiconductor. In reality, the silicon has a diamond-like crystal structure which is shown here on the extreme right. We're now going to look at the unending process of recombination and ionization that is always taking place inside silicon or inside any semiconductor material for that matter. The figure here on the left, figure A, shows the inside of the silicon material where each silicon atom has or it forms 4 covalent bonds with 4 neighboring silicon atoms. Figure in the middle shows that an electron, it leaves its place inside the valence shell. It leaves its place in the valence shell and it moves to the conduction band. So what happens is that a valence electron, due to, let's say, thermal excitation, it leaves its place inside the valence band and it moves out. It moves out into it goes, let's say, to the conduction band. Now figure C shows that the place from where a valence electron has left, a hole is created over there. So now what is a hole? a hole is basically a deficiency of an electron. So when an electron leaves, in place of it, an empty hole or a socket is created. So it's an empty vacancy basically, which has been created because a certain electron has left its place, leaving behind, let's say, a hole. So now what has happened over here is that an electron, due to, let's say, thermal excitation, it left its place inside the valence band, and therefore in its place a hole was created. So now this is the creation of an electron-hole pair, and this process is called ionization. Now I will revise once again. What is ionization? You must note here that ionization is a process that is always taking place inside a semiconductor at various locations, And what is ionization? It is basically the creation of an electron-hole pair, where an electron, it leaves a valence electron, it leaves its place inside the valence shell, and when an electron has left, due to, of course, thermal excitation, in place of it, an empty hole or an empty vacancy is created. Now, as the process of ionization is always taking place inside silicon, meaning that electrons are leaving their place in the valence band, moving to the conduction band, and leaving behind a hole. So as this process of ionization or this generation of electron-hole pair is always taking place, likewise, concurrently at the same time, through silicon, the process of recombination is also taking place. Now, what is the process of recombination? A recombination is that an electron in the conduction band, it falls into one of the holes inside the silicon. And now when an electron from the conduction band, it falls back and fills in one of the holes that was there inside silicon, an electron-hole pair is basically eliminated. Now this process is the exact opposite of ionization, and it is called recombination. Now the figure over here illustrates that the hole which was created in the previous slide has been filled in by an electron from the conduction band, whereas another hole is created at another location inside the silicon. A generation of another electron-hole pair is also being illustrated over here. So now it is important for you to realize that this process of ionization and recombination is an unending process, and it is always taking place inside an intrinsic semiconductor. Now over here on the right, you see the definition of thermal equilibrium. Thermal equilibrium is that at any given time, there are as many new electron-hole pairs which are being generated as are disappearing due to recombination. Now you see over here that small n denotes electron density, small p denotes holes density. Now the product of n and p is a constant. Or we can also say that in an intrinsic semiconductor, under conditions of thermal equilibrium, n, which is electron density, is equal to the hole density. Now this is also intuitive, because the number of holes are obviously equal to the number of free electrons, because it is only when an electron breaks free that a hole is created. So it is natural that the electron density is equal to hole density inside an intrinsic or a pure semiconductor. Now n with a small subscript I denotes intrinsic electron concentration. Now over here n, which is electron density, is equal to Ni, which is intrinsic electron density. Now we use this relation in this equation, that n multiplied with p is a constant, n multiplied by p is equal to Ni multiplied with Ni, and the product n multiplied by p, which is electron density multiplied with hole density, is equal to the density of electrons in an intrinsic semiconductor squared. As we move on further with the course, you will learn and realize that one of the special things about semiconductors is that the current inside semiconductors is carried by two kinds of charge carriers. The first is electrons and the second is holes. Now, while we all understand what is meant by the movement or the flow of electrons, we're now going to look at and understand what is meant by the movement or the flow of holes. Now, over here in the figure on the left, the silicon is almost like an insulator, as each silicon atom contributes one electron to each of the four covalent bonds with its four neighboring silicon atoms. The valence shell or outer shell are full, there are no free electrons, and hence the silicon crystal is almost like an insulator. Over here on the right, the generation of an electron-hole pair is illustrated. As the temperature of the system is increased, certain valence electrons, they gain enough energy to break free from the system, and as they break free from their place in the valence band, in their place a hole is created. Now you have to note that while electron-hole pairs are being generated, or let's say we know that generation of an electron-hole pair is called ionization. Now while ionization is taking place at several locations inside silicon, somewhere recombination is also taking place and electrons are filling in empty holes and the electron-hole pairs are eliminating. So that's something which you should also keep in mind, that whenever ionization is occurring, certain amount of recombination is also occurring. So coming back here to ionization, over here in this figure, generation of one electron-hole pair is illustrated. However, you realize that several electron-hole pairs at various locations inside silicon are being generated. Over here in the figure on the left, we see that there is a hole or a vacancy at position B, whereas there is an electron at position A. Now looking at the figure on the right, we see that the electron, which in the previous figure was at position A, moves in and fills in the hole or the vacancy at position B. Now because the electron at position A has now moved in to fill in the hole at position B, at position A, a hole has been created. So now what is the net effect? The net effect is that while the electron has moved from position A to B, the hole has moved from position B to A. So it's very important to note over here the movement of hole. So I'm going to repeat that because the electron, which was originally at position A, moves in to fill in the hole at position B. Now while the electron has moved from position A to B, the hole has moved from position B to position A. So now the situation is that there is a hole at position A and there is an electron at position C. The electron at position C moves in to fill the hole at position A. Now when the electron at position C left its place to fill in the hole at position A, its leaving of its place obviously created a hole at position C. So now the net effect is that while the electron has moved from position C to position A, the hole has moved in the opposite direction, or the hole has moved from position A to position C. Over here in figure 1, 2, 3 and 4, the movement of electrons and holes that we have been studying earlier is summarized. Over here in figure 1, this electron moves in to fill in this empty vacancy. We see here in figure 2 that as the electron, which was originally over here, had moved in to fill in the vacancy here, the vacancy which was present here moves in over here. Then in figure 3, another electron, which is over here, it moves in to fill in the vacancy which was generated in figure 2. Now as this electron at this location moves in to fill in the vacancy over here, it creates a vacancy in its position. So now you can notice that the important thing to note here is that the movement of electron is always opposite to the movement of hole.